speaker is Michael Brannan, and he will talk about quantum expanders from quantum groups, right?
Yes.
Yes. So whenever you're ready.
Okay. Let me just erase the board here. So, good morning, everyone. Maybe before getting started, I just want to thank the organizers, Matt, Laura, Christian, Adam, for putting on such a great conference. And maybe since I'm the last speaker, we should all give them a hand for their hard work over the past 5 weeks. Yeah, so it's been really an amazing opportunity for many of us to be here, and lots of fruitful outcomes. So, also I'd like to say thanks for the opportunity to give a talk here. Feels a little daunting giving the last talk. I'm going to talk about basically some work in progress, which is around the notion of quantum expanders. And property T. And this is ongoing joint work with Thijs Bernoy and Eric Kulf. And yeah, so the goal of this talk, I'll probably be a little light on the details given the time constraints and stuff like that. But what I want to talk about is really the notion of an expander graph in the context of quantum information theory. Okay, so expander graphs are examples of, well, regular graphs typically. And so the first thing I want to start off with is really, what is the quantum analog of a deregular, let's say, finite, undirected deregular graph? Okay. So such a graph, we usually write as G. It's got a set of vertices and edges. And associated to this, of course, we have an adjacency matrix, A. Okay, so this is the adjacency matrix. And A is going to be, if we have n vertices, then it's an n by n matrix. And being undirected, okay, we take it to be then self-adjoint. It's a 0, 1 matrix. And regularity really is saying that up to a scale, this adjacency matrix is a unital map, right? So A of 1 is D times 1. Okay. So this notion, of course, arose several times this week already. And in fact, we already heard in the context of quantum graphs what the analog is of a deregular graph. Okay, so one can talk about quantizations of graphs, and one can basically generalize all of these notions. So to sort of make this quantum, that's what you could do, but actually there's the consideration of quantizing deregular graphs that actually came in the quantum information theory community quite some time before the theory of quantum graphs, as we've seen this week, was popularized. So I want to sort of say a little bit about both ways of thinking about these things. So, yeah, the point here is this A here, if I rescale it, I get a channel, right? This is a bistochastic channel. And it's acting on, of course, the function space of the vertices, right? So this is a unital, completely positive map, which is also trace preserving for the canonical trace coming from the uniform probability on the underlying vertex space. Okay, so we have a bistochastic channel with some extra properties. But, you know, the analog of a bistochastic channel, of course, in the context of quantum information theory is, well, you consider bistochastic quantum channels on Mn, okay? So if we make this quantum, a natural thing to do is to consider a bistochastic quantum channel phi from now Mn to Mn, where I'm thinking now as my space of sort of quantized vertices, the matrix space Mn, okay? And so my channel, right? So in a sense, the channel associated to an ordinary deregular graph is sort of describing the graph in a dynamical sense. Really, it's describing the random walk associated to the adjacency matrix. And of course, the quantum channel is also often regarded dynamically, okay? So we can consider a quantum channel, which is bistochastic. And depending on the context, you may or may not insist on sort of symmetry of the channel with respect to the matrix trace, okay? So often, you may also assume phi is self-adjoint. So this is, you know, permission self-adjoint. Okay. So when I say phi star, I mean really the dual associated with the matrix trace, canonical trace. Okay, but this is not strictly necessary. Okay, so this is sort of a very sort of natural way to sort of go from what you get from a graph to something like this, but of course the things you get here are much more general, right? Unital completely positive maps are more general. And in particular, it's not at all clear maybe how you would generalize the notion of degree. So what would the degree of such a thing be? Well, what's often done in the literature is you declare the degree of the channel to be the Krauss rank of phi. Okay. So the Krauss rank of phi is you basically find a system of Krauss operators to represent phi of minimal size. Okay. So phi of rho will always have a Krauss representation. I equals 1 up to, let's say, d. And then we have xi rho xi star. Okay. So this is a minimal Krauss representation. Okay, and then d is the degree. Okay. So this is a natural way to think about quantizing a graph, although one might, given what we've seen earlier this week, say, maybe there's a better way to do it using the language of quantum graphs, okay? So an alternate way of doing this is to consider something that may be more true to sort of the notion of having a 0-1 matrix describing your channel, is to use quantum graphs. So consider quantum adjacent, deregular quantum graphs let's say Mn, or if you like more general, multi-matrix algebras. Let's say B. Okay. So here, now we consider a linear map from Mn to Mn, and we want this thing to be a quantum adjacency matrix. Okay, so this thing here is completely positive. Maybe, again, we want to think about real quantum graphs, so we will insist on an undirectedness condition, so we have it to be Hermitian with respect to the usual Hilbert-Schmidt interproduct on Mn. And then you also ask for this property, that the surproduct of A with itself be equal to A. Okay, and this is this sort of quantum surproduct. Okay, which for Mn being replaced by B equal the diagonal matrices, this is really just entry-wise multiplication of the matrix implementing A, and otherwise it's more complicated, and you have to impose some information like a state on the algebra Mn. Okay, so this I guess we've all sort of seen before, and deregularity again is just this condition right here, right? So we say it's deregular if this is the eigen, the unit is an eigenvector. Okay, good. So what are some examples of quantum deregular graphs? Maybe the sort of, if you could think about this first way of quantizing things, well, you just got to write down some unital channels, right? So one way to do this is random unitaries. And maybe we might want to think about classical and quantum versions. So random unitaries are very natural, or rather I should say mixed unitary channels. These are natural examples. Okay, so for example, you just take phi of rho to be, let's say, 1 over d times sum over I equals 1 up to d, ui rho, ui star. Okay. So this in general will not be a Hermitian channel unless the maps are chosen appropriately. And of course, there could be some redundancy in this representation. Right. So the degree is not necessarily what I wrote here, but one could, in principle, compute this. So these are sort of natural examples that arise this way. And kind of one of the things I want to sort of point out is that a lot of the examples that one encounters are sort of random unitary-like. And in particular, I want to talk about, if you think about quantum groups, somehow most channels you encounter in life, including ones that are known to be non-random unitary, are still sort of this flavor where now we look at essentially matrix valued unitaries as opposed to scalar valued unitaries. Okay, but that'll come up in a few minutes. What I want to say now is, of course, classical deregular graphs. Where do these come from? Well, a natural way to construct these is by looking at Cayley graphs of groups. Okay, Schreier-Coset graphs as well. Okay, so gamma is a group. Okay, and let's say gamma has a symmetric generating set which is finite. Okay, so S is a subset of gamma, which is symmetric. And let's assume that the unit element is not in S. Okay. Gamma could be finite or infinite. Of course, the Cayley graph can be made sense of in any case, right? And the Cayley graph associated to S, this is the graph whose vertices are the elements of the group, and the adjacency matrix of the graph is, well, informally we can write this as the sum overall gamma in S of the translations by gamma, okay? Where I write lambda of gamma, meaning really if I think about the adjacency matrix as acting on the Hilbert space of square summable functions on gamma, it really is the left action corresponding to the generating set, okay? And this is a regular graph. And the regularity is, of course, the size of the generating set, okay? Okay. So this in general, of course, if the group's infinite, will give you an infinite graph. But you can, of course, start with an infinite group and maybe find a finite index subgroup and look at the coset space, and this will induce from this infinite graph a finite graph of degree d called the Schreier graph. Right, so if, let's say, we have a subgroup of gamma, finite index. We have a finite index subgroup, then, well, what we can do is consider the Schreier graph, which I'll still write as Cayley, of the quotient. Now the set, on the vertex set is going to be the quotient space. And S again is our generating set of the original group. And so here the vertices are just the set gamma mod H, which is now finite, and the adjacency matrix of the graph is sum over gamma in S again. But now I consider the natural translation action of gamma on the coset space. Okay. So these are a way you can go from a general infinite group to constructing an associated finite regular graph. And in some sense, lots of graphs that appear in nature are actually of this form, deregular one. So I think if the graph has even degree, you can always realize it as a Schreier coset graph. Okay. So yeah, so classical ones, you know, so there's a very natural algebraic way to realize them. The sort of canonical unital quantum channels that you see in nature and in practice are random unitary ones. And sort of one of the things I want to tell you is how you can kind of quantize this Cayley graph situation, while at the same time sort of encapsulating something of this type, okay? So let me just mention there's a common framework of these quantizations using essentially discrete quantum groups. Okay. So you can imagine sort of how this is going, because on Thursday, I guess yesterday, we learned a little bit about Cayley graphs of discrete quantum groups. Okay, or in the context of the Mateusz's talk on Thursday, it was finite quantum groups, but the theory sort of goes through in the same way. And the idea is as follows, okay? So what's a discrete quantum group? Very vaguely, so this is a discrete quantum group. So what's this going to be? Well, an ordinary group, a discrete group, is of course a set, a discrete set with a multiplication rule, which has some additional nice stuff associated to it. And I want to think of this at the level of function algebras instead. So instead of telling you a group with a multiplication, I'm going to tell you what the algebras associated to it are. And L infinity of gamma, well, this is usually just a direct sum of one-dimensional spaces, one fiber associated to each point, right? But now we sort of allow each fiber to be a matrix algebra. Okay, so I consider the bounded direct product of matrix algebras. This is sort of the function algebra associated to a discrete quantum group. And we have a nice co-multiplication. And this is this unital normal star homomorphism defined on this algebra, which is co-associative and what else do we have? And then, of course, together with this, there's some additional stuff. In particular, there's Haar measure. And here I will assume for this talk that H is a tracial Haar measure. So this is the context of unimodular discrete quantum groups, which is kind of a surprising thing if you've never seen discrete quantum groups before. So discrete groups, of course, the Haar measure is canonically just the counting measure, which is obviously tracial. In this case, it turns out you can have non-tracial things, but for the applications I want to consider, the ones with tracial Haar measure are the ones of interest anyways. So in this case, you can really write down the formula, and you saw this in Mateusz's talk. The Haar measure is this weight, which is sum over gamma, the dimension of gamma, times the unnormalized trace on MD gamma of C. All right. So there's this Haar measure. This is like an analog of a translation invariant measure. And translation invariant measure is recorded with this co-multiplication. Okay, so this is roughly the idea of a discrete quantum group. Yeah, so how do you associate channels to, or quantum graphs in a sense to discrete quantum groups? Well, we say, so we have this index set here, I, right? This is this fixed index set which describes our sort of discrete structure of our space, okay? And we say that a finite set S inside of the index set I generates our quantum group gamma, okay, if, well, what we do is we look at the central projection supported on the index set S. So this is this direct sum of identity matrices over the blocks gamma in S. Okay, this is a central projection, and as we saw yesterday, I can take convolution powers of this projection. All right, and then I can look at the supports of this convolution powers, and if I keep taking convolution products, this is going to have to equal, for a generating condition, the entire unit of the whole thing, okay? And again, this is sort of, okay, even if you don't really see these definitions of discrete quantum groups, generally, this is sort of like an expected kind of notion of generation that you would get, right? So you have a projection is an analog of a subset, and a set generates it if, I multiply things together enough times, I will eventually cover the whole space, okay? And usually we'll also assume that it's a symmetric set. So there's a notion of kind of dual, which is kind of playing the role of inverses in the quantum group case. And we will assume also that sort of the trivial object is not inside of here. Okay? And so how do you construct channels from these things? Okay, so construction one is you can look at, of course, the quantum Cayley graph associated to a projection supported on this. So take, for example, P, let's say equal to 1s, okay? And you can define A, this is going to be a, in general, unbounded operator on this von Neumann algebra, okay? But it sort of makes sense if you restrict to sort of finitely supported elements of this algebra. You can make sense of everything. And as we saw with the talk yesterday of Mateusz, A of x, which is given by convolution against x by this projection, okay? This is a going to give us this Cayley graph associated to the discrete quantum group NS. And let's say actually, yeah, I'll just say S. Okay, so this is this quantum Cayley graph we saw yesterday. Okay, and this is D regular with D equal to basically the sum over gamma in S of the dimensions of the matrix algebras associated to. Yeah. Yes. So this directly generalizes the usual case. In the classical case, the fibers associated to these points in the generating set are one-dimensional, so you're just taking the size. Here you also capture this thing here. It's self-adjoint if, well, yeah, I mean, it will be self-adjoint because of this symmetry. Okay. So this is a way to get a Cayley graph out of any discrete quantum group, and it'll be a finite Cayley graph if it's a finite quantum group. In general, though, I mean, how can you do a Schreier graph? Well, this is a bit of a strange thing. So a quantum analog of a Schreier graph the idea here, and maybe since I'm running low on time, is to look for the analog of the function algebra of gamma mod h, okay, where h is now a closed quantum subgroup, okay, inside of, and so naturally, you know, functions on cosets can be realized as subalgebras of the original algebra, okay, and here, if we want to think about this thing, it turns out the natural analog in the quantum case is coideals. Okay, these are generally von Neumann subalgebras of here, okay, which are covariant or invariant with respect to the co-multiplication. So this is B inside of L infinity of gamma, which are satisfying the condition delta of B is contained in L infinity of gamma tensor B. Okay, so these are what are called coideals. And what's kind of interesting is, in the quantum case, these types of objects are much more general than quotient spaces. One can make sense of quotient spaces in general, but the theory of coideals is much richer. But nonetheless, whenever you have something like this, so given B, right, you can restrict A to B because of this covariance condition. And convolution really means that B will be an invariant subspace, and you get a quantum Schreier graph. All right, so problem examples are very hard to find. So in particular, we'd be interested in finding genuine quantum Schreier graphs, which are finite regular graphs. So this will be, this associated restriction operator will play the role of an adjacency matrix on a finite d-regular graph. But finding examples with this property sort of seems to be a bit of a troublesome task. But in any case, this is sort of the natural thing you would do if you want to talk about the Schreier graph construction. The second construction is...
Like, for gamma finite group, wouldn't this just be the Church projection multiplied in the Liga subvector that you get by taking the cross product with the
Yeah, I think so.
group H? Because that we think of that as being the analog of the quotient space.
So yes, the Cayley graph, but it would be associated to a particular choice of a generating set. I believe it would be the generating, it would be the generating set associated to the entire finite group. Take S equal to all of gamma. Yeah. So another way to do this is to consider unitary representations. Okay, so a unitary representation of a discrete quantum group. Well, what is a unitary representation of a group? Well, it's a family of unitaries indexed by group elements. So it'll be the same thing, but now we have our index set. And this is not going to be a scalar unitary, but instead it'll be a matrix unitary. Okay, so this will be each U gamma is unitary in M d gamma tensor B of H, and this is going to be a representation on a Hilbert space H. Okay, plus some conditions which make it, behaving like a multiplicative map. Okay, but I won't specify what that is because, right. So again, I'm going to think about my quantum group as being, finitely generated. We've got this generating set, and you can get a random unitary channel, well, a random unitary-like channel. It won't be random unitary in general, by doing the following. Okay. So take a faithful state, and okay, I'm going to say faithful in a not quite precise way, supported, so it'll be phi, on L infinity of gamma, and I want it to be faithful on essentially the corner, or the cut down of my algebra by this central projection. Okay? Okay, so I take essentially a state of full support contained, inside of S. Okay. Right. And then what I can do is I can form a channel associated to my representation, coming from phi and U, which is kind of mimicking this sort of random unitary construction, which is going to be, what I do is I take my input state on H, rho in B of H is going to be finite dimensional, and I conjugate by U. And then I basically average this conjugation against my quantum probability, phi, right? Fact, if our group is quantum group is unimodular, this is a unital quantum channel, even when phi is non-tracial. So this is a unital channel. And this is essentially coming from the fact that in that case, this U is a biunitary matrix and not just a unitary matrix. Okay. get a unital channel, and not obviously, I will say, random unitary. In particular, non-factorizable maps can be represented in this form, in certain examples at least. So you know this construction produces something more general than random unitaries. And in the last bit, I just want to say now, what does expansion have to do with this talk? Okay, so if I take a deregular graph, right, I can talk about it being connected, and I can also sort of measure how good is it, or how efficient is it at being connected, in the sense that I maybe have small degree, but connected, and the efficiency of this sort of connectedness is measured with what's called the Cheeger constant, this expansion constant, which really says, in a sort of concrete way, how if I take like a relatively small set, which is not empty, and not the entire vertex set, and I look at its boundary, these are the vertices with edges exiting my set. If I have a relatively large boundary, given the size of my set, okay? And I will maybe also incorporate the degree into that, okay? So this is what's called the Cheeger constant of phi, or for graphs, it's really measured in terms of graphs, okay? And since I'm running low on time, this is really by these Cheeger inequalities coming from the spectral gap of the channel phi. Okay, and what we have is the following. Phi has eigenvalues, and the largest eigenvalue of its self-adjoint is 1. And then we have a next smallest eigenvalue, lambda 2, and all the way down to, let's say, lambda n squared if it's a channel on Mn. Okay? Cheeger inequality. And Cheeger inequality says that good expansion is really equivalent to saying that 1 minus lambda 2 is bigger than 0. Okay? Now this is sort of a vague statement. Generally what you want to have is a sequence of graphs where this spectral gap for the associated channels is going to be uniformly bounded below, but at the same time, well, you want the degree to be fixed for the family of channels, okay? So the problem in general in quantum information theory, and actually originating from graph theory, is to find quantum expander families find quantum expander families. So this is really phi n, deregular, all of them. The n going to infinity. This is Mn being the vertex space. And, well, what we want is that this 1 minus lambda 2 of n is, let's say, bigger than some bigger than some epsilon for all. Okay. All right. So I'm out of time, unfortunately. So maybe just in one minute, let me just say, I mean, how do you sort of construct these families? So in quantum information theory, you can look at random unitary channels. So you look at mixed unitaries and consider random unitary Krauss operators, and probabilistically you get these things very concretely. But in the classical theory, one has this notion of expander graphs coming from property T groups. Okay, so property T is sort of a representation theoretic rigidity result for discrete quantum groups. This is actually a theory that just works perfectly well, and this ensures uniform spectral gap for channels for quantum Schreier graphs. And this sort of construction, and construction too. Okay? So I'm out of time now, so maybe I'll just say, what was our hope with this project? So it was sort of expected that sort of the theory for discrete quantum groups would work the same way. And this would give, okay, a new way to sort of construct non-random expanders. And so what can we do? Well, there are lots of new examples of discrete quantum groups with property T. And some of them you can examine. These are usually called bicross product quantum groups. And for those, we can construct genuine sort of non-random unitary, what seem to be non-random unitary expanders. But, well, they're sort of in a way not so far from being random unitary for the examples we have. And somehow the hope is that this kind of use of representation theoretic methods might actually give some sort of new classes of examples. But that's sort of to be determined. So I'll stop here. Thank you very much.
Any questions or comments?
Have you managed the Margulis construction for to obtain the expanded graphs from the property T quantum groups?
Yes, yes. So this is, right, that's right. So essentially, this channel, for example, this unitary conjugation channel, this, right, I mean, essentially, this conjugation is also a unitary representation, so property T will ensure a spectral gap. And from that, you get analogs of the Margulis construction. Also for this Schreier graph, this co-ideal thing, you can use the unitary implementation to get spectral gap from that.
Then the proof is also similar, like using a Kasdan constant and...
Exactly, yes. So the Kasdan constant is, yeah, it's the same. Yeah.
Okay, thank you.
Yes. But the construction of discrete quantum groups work is easy, but you construct these channels, you say is there any information theoretic about these channels? That's sort of interesting.
So information theory, I mean, I guess, which are actually, so it, I mean, I guess one question would be, is the, you know, what are expanders used for in the quantum case? Is that the question you're asking? Or it's particular about these constructions?
I mean, correct me if I'm wrong, but I'd say you're constructing channels, right?
Yeah, yeah.
I guess you're kind of maybe interested in sort of like, are they depolarizing?
Yeah.
Or I don't know. Like
Yeah.
That's more
Yeah, so these, there's, yes, very natural questions one could ask about these in particular cases. And I think the general construction, you really have no idea, but in specific examples, you know, you take particular functionals like phi and you have a particular Kasdan set, so you know actually which sort of unitary blocks are going to be used. And in that case, you can say things. But I think a general statement, I don't know.
Would a central version of property also be useful?
Pardon me?
Would a central version of property
That's a very interesting question because in a way, central property T is easier to find in the tensor category world, for example. And this is a question I discussed with Dietmar actually, is whether one can sort of work directly in the setting of unitary tensor categories and try and find property T related channels that way. But to be determined, yeah.
Any more questions? Okay, then let's thank the speaker once more.